So, good morning, everybody, to this morning's webinar about carbon and sulfur detection in steel and other metals. Today, we are looking forward to a webinar focused on a certain application, carbon and steel in metals. And the webinar will be held by myself. This is Kaan Toprak, export manager at Ultra, and our sales director, Andreas Theisen.
Good morning. Hey, we have a lot of people attending. I know that for some of you, it's very early. For others, it's very late. So thank you very much for attending our webinar here.
Yeah, and besides Andreas and me, we also have our product manager here, Mr. Mike Lucker, who takes care of the chat and also of the technical background. It's looking like a TV studio here a bit, so quite a bit to do for this guy. He will later on say hello to you as well. Okay, so let's start the webinar. Today's topics will start with a welcome to Ultra, followed by our overview of effects of the elements carbon and sulfur in metals. We will present you the most typical sample material we are working with and also the working principle of the analyzers. We show how you may optimize your results and your analyzers, and present also some typical results that are gained with Ultra analyzers. And last but not least, there will be a discussion. How does this discussion work? You realize that most of you are muted, not because we don't want to hear you or get some input on you. No, you are muted because otherwise it will be very chaotic if everybody speaks at the same time. But for your input, we have a solution. It is a chat box. You can see a chat box and you can activate it and immediately put your question there. Online is Mike, who will answer your questions directly or maybe with a little delay, depending on the amount of input that we get here. And later on, we will discuss some of the question representatively inside our group to give you the answers as fast as possible. Please understand if your questions should be a little bit more complicated, we might do it later on by sending you an email or additional material. Also, I would like to tell you in advance that at the end of this webinar, we will make available for you a download package of valuable information, hopefully valuable information with regard to CS analyzers in metals. So Ultra is located here in the western part of Germany between the lovely cities Cologne and Düsseldorf. We are established in 1981 and our portfolio covers mainly elemental analyzers for carbon, sulfur, hydrogen, oxygen, nitrogen. Also a very successful thermogravimetric analyzer, TGA, macro thermogravimetry, and of course, high quality consumables and accelerators. At the moment, we are sitting right here. Not so many clouds today, but lovely weather. And we are directly here where you see the laser pointer. Our offices are located there. Yeah, thank you for attending this webinar. As I said, we do it online, but and hope very much that in future we will have you here as our guests as well, or visit you in your places to make this webinars again as a real seminar in real life. Okay, CS testing in metals has many facets. It is used for quality control in steel, also together with the production of steel and to test starting materials. It is used in refractory metals like titanium. For mining, CS analysis is very important to see the quality of the ores and the products. Aviation industry is mainly quality testing because there you have to make sure that all the parts used in the plane are stable and have the expected quality, of course. It is used in metalworking industry in general. in wires to have a good conductivity and the pure elements. In research, of course, in medical engineering, and during the last years also in 3D printing, additive manufacturing. There we realized that we have a new type of sample increasing its powders, metal powders, different types of alloys, which are tested before using them for the 3D printing, but also the final product is tested as well to make sure that the quality of the manufactured product is as expected. It is tested in so many applications because carbon as well as sulfur have some effect on the metal. We will not show you all the effects of all metals, but we picked steel as one of the most common testing materials as an example. If you look for carbon and steel, you would find that raw iron has about 4% of carbon content. High carbon steel, larger than 2.1%, is very brittle. The product is not ductile at all, but it's a very hard type of steel. If you control the carbon content between 0.2% and 1.7%, you can control the hardness. If you need a quite hard steel, you would select a higher carbon content. For a less hard steel, you would go lower. And with a lower content than 2.2%, the steel is no longer hardenable. It is very ductile. And of course, all types of steel, very hard one, middle one, or even softer metals, is required by industry for certain applications. It is the process of manufacturing where the carbon content is defined, and it is the topic of the quality control with ultra CS analyzers to determine the real content and to ensure the quality and the properties of the material. The effect of sulfur in steel is a little bit different. Sulfur in general increases the machinability of the steel, in explicit how it might be drilled or milled. The higher the sulfur content is, the lower is the ductility of the steel. And also a high sulfur content combined with low carbon and low manganese steel has an effect on the surface quality. The surface gets, gets affected, is harmed easier if you have a higher sulfur content. So also the sulfur content in metals must be controlled. For that, the customers take their samples and put them in general in elemental analyzers like ours. I will start showing you typical sample materials. From on the upper row, you can see a kind of more powder or grain-sized samples. Very fine. On the left side, this is tungsten carbide, a powder which is freshly sintered. Here we have typical steel shavings. The easiest way to make some metal small is simply drill it, use the drillings and put in the analyzer. Here we have some grains of different sizes, fine or grosser. We have raw iron here, and for calibration, we use pins like this one, or some drillings or rings. All of that is possible to be used to calibrate the machine and to be analyzed with the CS analyzers of Ultra. A typical sample is also if you take one of these plates, which are usually used for spectroscopy, and simply pinch a small part outside, and you can immediately, without further preparation, use it for the elemental analyzers or by cutting a piece of those tubes. Sample amount is typically between 50 milligrams if you use very little amount, up to 1 gram, very much depending on the application and what the customer likes to use. So it's not very sensitive here. We can offer you a broad range of typical sample amounts that you can use. Do you have further questions about the samples? What kind of samples do you have? You might ask that in the chat. Mike will answer it. And now for the next slide, I'm handing over to our sales director, Andreas Theisen, who will start explaining the working principle of the analyzers.
Yes, thank you very much, Khan, for the introduction. So I would like to continue explaining you how the typical elemental analyzer works. And later we will come to the point, what can I do to get best results? But first to the principle. The principle of an elemental analyzer is quite easy. So what we do is we have the sample. We put the sample in the crucible. Which is a ceramic crucible. It is only one-time use, so you throw it away afterwards. And then you heat the crucible up in the furnace. This is very important to get a high temperature, first because you want to combust the sample, and you need a certain temperature to combust. And on the other hand, you also want to melt the sample, because it's very important that the sample not only burns on the surface, but that the whole sample melts. And then afterwards, when it's melted, that then the burning process starts, or at the same time. But it is very, very important that the sample will melt during the burning process. So then we burn the sample, and most of the parts of the sample will stay in the crucible. So the metals will have their metal oxides, which are solid afterwards. Only elements like sulfur, carbon, and some others, which I normally don't have in metals, they will be gases, reaction gases, and they will taken with the carrier gas to the detectors. In our instruments, which we are talking here about today, we look at CO2. CO2 is carbon oxidized by the oxygen stream, and SO2. SO2 is sulfur oxidized by the oxygen stream. And then these two gases come to the detector, and the detector is looking at these special gases, so it can distinguish between CO2 and SO2 so that they don't influence each other. And from this signal, the detector makes the signal which we see in the detector, we come to the result, to the concentration of our element carbon and the element sulfur. Let's look at the next slice, how the furnace works. The furnace is the important part for getting our gases, which we later detect. We have a temperature in an induction, it is an induction furnace, so it's comparable to your induction oven you have in the kitchen. So you have a magnetic field which changes very quickly the direction, plus minus, plus minus, plus minus, and due to this, the magnetic particles inside your metal start to move, and with this you get the heat inside. And with this induction furnace, you get very quickly a very high temperature inside the sample, and when switching off, the energy is off completely. So you have a very quick cool down process. The temperature which we can reach in such an induction furnace only by heating is 2200 degrees, something around this, depends on the metal, of course, how good it interacts with the magnetic field. For some metals, this is still not enough to melt them, but keep in mind, we will also have the heat of induction, the heat of combustion later, which means that when the sample combusts, we get additional heat. And this brings us then to the point that the sample will melt completely. The carrier gas is oxygen. It's pure oxygen. Normally, we advise 99.5%, which is a normal quality you can buy everywhere in the world. We have some accelerators. I will talk later about this, what it means, why do we need them. And the typical application is, that is what we are talking here about, carbon sulfur in steel, copper. It's not only for metals, you can also use this for glasses, you can use this for cement, you can use it for ceramics, but this is something we will not talk about today. Here you see a typical signal you get in the detector. So you get one signal for carbon and one signal for sulfur. In fact, if you have the fully equipped instrument, you have 4 detectors, 2 for sulfur, 2 for carbon. And this is because we have we need 2 detectors to cover the whole concentration range, because the length of the measuring cell is part of the physical signal I get later. The longer the length is, the more sensitive my detector is. And this is the reason why I need 2 different lengths of detector cells to cover the range from, let's say, 5 ppm to 100%. We are looking with infrared light in our cell, in our cuvette here, and the infrared light is absorbed, and the more concentration of these gases I have inside my cell, the less light is coming out again, the more light is absorbed, and from this signal I have a direct connection to the concentration in my sample. It is a molecule-specific signal I already mentioned. So this is very nice because, in fact, we can measure in a mixture of SO2 and CO2, we can measure only CO2, so we don't have to separate them first. Some elemental analyzers work different. They separate the gases before they measure them. This is a bit more complicated because you need a lot of chemicals. We don't do it like this because this is much more straightforward to measure them in a mixture at the same time because of their specific extinction coefficient to infrared light. And the principle is infrared absorption. Okay. How does it work in practice? So how does it work in your laboratory? It's very easy. Of course, you have a software. Then you weigh in the sample. You need the weight of the sample because the signal later refers to the initial weight, because you get a concentration, not a absolute mass, but you get a concentration. Then if the sample is in the crucible, you put it in the furnace, and from then on, everything is doing automatically, and at the end, you get your result. The nice thing with elemental analysis is the typical short analysis time of 40 to 60 seconds for the signal itself. Then you need some time to purge the furnace after you close it again. So let's say overall, one measurement is done in 1 minute to 2 minutes, depending on how the temperature is and what type of sample you have. This is a nice picture my young colleague put in. So you see a picture from the computer. No, it's not computer, it's Nintendo, it's Zelda. And it's a very old game. Even I played it when I was young, which is 30 years ago or more. So here in this, it's dangerous to go low to this. Here, normally Zelda gets a sword, but we need some accelerators to get better results. Why do we need accelerators? There are 2 reasons for this. One reason is to moderate or to accelerate the burning process. Here you see a typical result. This is a sample which produced a lot of dust, which came out of our crucible, and the temperature at this local point was so high that the crucible cracked. This is something you should prevent. So this is something which comes from the point that the sample burns too quickly. So if you optimize the parameters by using moderators, by using a lower temperature, then afterwards your crucible looks like this. This is after the burning process, the black gray, the gray residue you see here at the bottom is our metal oxides coming from the steel, from your metal, and the gases already came out. And this is how your crucible should look like after the burning process. Then you did everything correctly, and then you will get very nice results. Might be that you get good results here too, but here you have to clean everything after 5 measurements. This is why we don't recommend to do it like this. Always try to have it like this. And you see also here that you have a very nice surface. If you still see your sample here, then it means that the temperature was not high enough. Your sample is not melted completely. So let us see what we have to take in account when we make our measurements. Rule number 1 is, which you should really keep in mind, is never touch the crucible. For 2 reasons. One reason is it might be hot. This is very, very, very dangerous because the color of the crucible, it doesn't show you in every case that it is hot. If it is very hot, then it is red, but if it is not red anymore, it doesn't mean that you can touch it. And this is because this is one reason why you should always obey the rule, never touch a crucible. Of course, the other reason not to touch a crucible, especially if you work with low concentrations in the ppm range for carbon, is because the grease or fat on your fingers will diffuse inside the crucible, and you will measure them additionally to the carbon content in your sample. Rule number 1, perhaps the most important rule. Rule number 2 is use accelerators, moderators. On the next slide, I will go more in detail with this. And then we have a third rule. This is also if you want to measure very low concentrations, then preheat the crucibles before using them. This is a ceramic, and the ceramic, all ceramics, they tend to solve CO2 coming from the air, absorb CO2 inside their structure. And this CO2 you can get easily rid of if you preheat the crucibles in a furnace. This is a tube furnace. So you put in a crucible here, and then you put, every time you measure, you put in the next one, and it will come out here. Another possibility is not to make it, so to say, online to your analytical process, is that you take a muffle furnace, put in 50 crucibles, preheat them, and then later on you put them in an exsicator where it is stored without touching the atmosphere again. And the typical temperature which you should use for preheating the crucibles, which you find in some standards too, is 1000 degrees centigrade. You cannot do it in your normal drying oven. Please use a special oven furnace which reaches temperature in the range of 1000 degrees. This will improve your results because you lower the contamination, and it will save your fingers for burning them. Then we have the accelerators. So I will talk a bit about this because this is now a bit more, let's say, complex, but at the end it's easy. Yes, because it's like cooking. Yeah, you have to learn when do I use which accelerator, but if you know once, then you can use this as an SOP, standard operation procedure, for your metal, and then you don't have to change it again. The first and most important accelerator moderator we have is tungsten. Tungsten is a metal with a very high density. The density is more than 10. I think it's even 20. So it's very dense, which means if you put it on your sample later on, it is like a lid on your sample, which prevents that part of your sample sputters. Yeah, you know, if you look at fireworks, for example, if you burn metals, this is the typical firework. Here in Düsseldorf, we have once a year Japanese firework, and you see these nice stars and flowers done by metal powders which are burned, and these sputter all around in the air. And this is something, of course, you want to prevent here, because it is something which will make your furnace dirty and which will give you lower results because part of the metals are no longer inside your crucible. So this is The moderation of combustion, which we have here, is because it's like a lid on your sample. On the other hand, tungsten burns with a very high combustion energy. So you get tungsten oxide, and tungsten oxide, when tungsten burns or oxidizes to tungsten oxide, then you get a lot of additional energy, additional to the energy you get from the induction field. So it's a very nice metal to get better results when melting the sample. So you get higher temperatures, higher than the 2200 degrees. Then we have iron. Iron is also very common used if you have substances, if you have metals which do not interact with the magnetic field too good, especially, for example, if you have ceramics or if you have cement, but also for metals, for example, if you have steel, let's say pig iron with a very high concentration of carbon, then also the interaction with the magnetic field, with the induction field is not very good. And then you put iron to it. So you mix your sample with iron, the iron melts, the iron burns in combination with the induction field. And this energy, again, is enough to melt your sample so that it will burn too afterwards. So tungsten and iron are the most common metals which we use as accelerators. There are more. And one of the also very common metals is tin. This ultracell here is a mixture of tin and tungsten, and you can also use tin and put tungsten then later on it. The tin is a very good flux metal, so we also use this in our other detectors where we measure ONH for the measurement of hydrogen. Tin lowers the melting point of many metals in a dramatic way. And this is why we normally use it. You see it here, especially for the so-called refractories, which are normally very high melting metals. Yeah, they have a very high melting point. We put tin to these metals to lower the melting point to get an eutecticum. The disadvantage of tin is that it produces a lot of dust inside the furnace, and to avoid this, I will show you on the next slide. We have, for example, we have lids so that the dust is not coming out of the crucible. The third or fourth metal we use normally is copper. But copper can only be used. It's very nice because you can get it easily, very pure. Yes, copper is one of the metals because of the copper wire industry, which you can buy in a very pure way. So we normally use this for our ceramics, where we need very precise and a very good reproducibility, like tungsten carbide. But you can use copper only if you are not interested in sulfur, because you will find less sulfur because the copper tends to absorb the sulfur. Coming to the next slide, you see some more things we have. For example, the crucible lids. I already talked about this, especially for fine powders. So the one reason is that they are blown out of the crucible. The other reason is if you have fine powders, normally you get dust, and to avoid that, the dust will get out. So also for powders, we have special solutions. And this is something which is very important if you work with metal powders, especially in, for example, in additive manufacturing. Okay, thank you very much. So let me continue. I have one thing I would like to stress, and this cannot be stressed enough, is the results you get in an elemental analyzer depend very much also on the freshness of the chemicals. So it is very important to change the chemicals from time to time. And this, again, depends a lot on how much sample throughput you have. We have here in our analyzer two chemicals which are very important. First one is magnesium perchlorate, which is also called anhydrone. And the word anhydrone already tells you what it does. It absorbs water, because water is a very nasty molecule. because it has a broad absorption in the infrared detector, so which means that it disturbs all of our measurements. We have to be sure that we get rid of the water before our gases come to the detector. So we have 2 points where we have the perchlorate. One point is here at the beginning where the gas comes in. In some countries, we have quite poor gas qualities. And this is the reason why we always have for the incoming gas also a drying step where the water is absorbed. And then we have a second absorption after the furnace, which means sometimes you will have, your sample will be perhaps have a bit moisture, especially if it is not a metal, but sometimes you have some, for example, hydrogen inside your sample. And when this burns, of course, you get water too. And this is why we have another step after the burning process, after the furnace. The other chemical molecule we want to get rid of is CO2 coming from the gas, from the initial gas. As I said before, normally we take a quality of 99.5, which means 0.5% of the gas coming in is not oxygen, but something else. And most part of it is CO2. And this is absorbed here by sodium hydrogen, so-called ascarit. You see here it is black. Sometimes it's gray. What we sell in the moment is gray. So it doesn't depend on the color. So don't be puzzled if you don't get black one or if you get black one. The important thing is that this sodium hydroxide absorbs CO2. Important now, one thing is really important. Be sure that you put it in the correct direction, because when CO2 is absorbed by sodium hydroxide, the reacting gas is water. So you have first CO2 absorption and then water absorption. This is very important because otherwise you will later on have water in the furnace, which is not very good, because then this trap after the furnace will be used very, very quickly. So always be sure that your chemicals are fresh to get best results. If you have a real poor gas quality, then you can also use our gas purification furnace, which cleans the gas before it comes inside the analyzer. And for high throughput and the CSI, the induction furnace instrument, is a wonderful instrument for high throughput because it works and works and works and works without any problems over the day, over the night. We have the 36 and the 130 position autoloader. This is new, we have it now new, the big autoloader, so that you can measure a lot of samples overnight. Then we have a vacuum cleaner. The vacuum cleaner option is always coming with the instrument, which means you can attach a vacuum cleaner, which you have to buy separately to get out the dust out of the instrument, which we normally propose for samples which are dusty. So you have to check by yourself if your samples are dusty when they are combusted. We have the halogen trap, also very important if you work with samples containing halogens. So then it can be trapped here. We also have the possibility to provide solid gold cuvettes so that the cuvettes are not corrosive against halogens. One thing which is very special with our instruments and where we are very happy to have it because it is really effective is that we have the possibility to switch off the lens, the oxygen flow through the lens. We have 2 flows inside this is now the furnace, and inside is the crucible. You see it is hot and oxygen is coming around here. And at the same time, oxygen is coming here through the lens directly in our crucible. For many samples, perfect because you have a direct oxygen stream to the crucible. But sometimes if the density of your samples is low, you have powders and you have a lot of dust, then you would like to avoid this. And then you can switch it off here. So you can go from solid to dusty, and then you switch it off here, and you will have a lot of less dust, and your powder samples will stay inside the crucible. The peak becomes a bit broader because the combustion process needs a bit longer, but on the other hand, you are sure that you can use, for example, an autoloader overnight, and your furnace will be clean at the next morning because you have much less dust inside your furnace. This is especially if you use accelerators like copper or tin, as I mentioned before. And which you can also do with our analyzer, you can lower the combustion temperature. And this is also important if you work with low melting metals, which normally have also a low boiling point, to avoid that you get temperatures, let's say, in the range of 2,400 degrees centigrade. Then your metal will start to boil inside the crucible, and then it will condense somewhere here. And this is something you should prevent. And you can do this by going down with the temperature. The same for high reaction material like magnesium. Perhaps you see here all the settings we can do for one measurement. Perhaps they sound all a bit difficult. Which type of accelerator should I take? Which type of flow? Which type of oxygen flow? Which type of, shall I use a vacuum cleaner or not? Shall I use ramping? We can also ramp the sample, the temperature inside the sample. When should I start with the measurement? How long should I purge? And so on and so on. We have the whole flexibility in our settings here, but we have also predefined settings which fit most 95 of all applications you will have. And we have a lot of applications nodes which will help you to find the correct settings for your application. Like a cooking book, yes? You can see every step in our application node you see to get perfect measurements. This is all done once for your sample. It's like an SOP, like a standard operation procedure. If you have done it once, you never have to change it again. There are two more analyzers, not only our induction furnace model, which I like to show you here before I switch over to Khan again. The first one is the so-called CSD. The D is for dual detector. Dual furnace, sorry, for dual furnace. So we have two types of furnace, not only the induction furnace, but also resistance furnace. Resistance furnace has a much lower temperature, and a resistance furnace, you can control the temperature much better. For example, if you want to look at the free carbon somewhere, which is not the carbon which I see when I combust the whole sample, but only which can be, for example, get out by raising the temperature, then you can use a resistance furnace. And resistance furnace much better for, let's say, substances like coal, for example, because they have a much lower burning point. So that it starts burning is at a much lower temperature. It's like you would never boil an egg in a pizza oven, won't you? And this is the same here. If you have sample which burn at very low temperatures like coal, you would not use an induction furnace for it because the burning process would be too quickly. Then we have the surface C800, and this one looks only on the carbon on the surface of your sample. So if you have, for example, grease on your steel plate, you will see only the grease, or on your copper tube, then you will only see the grease, not the carbon fixed inside your sample.
I will start with tungsten carbide. Tungsten carbide is not a metal, of course, it's a carbide. It's a metal metal molecule, but it is part, or it's one of the steps for the tungsten production. And we are very proud at Ultra that with the new CSI, with the new lens management of the analyzer, we are able to measure the carbon content in tungsten carbide very precisely. Why is it so important? Tungsten carbide is a carbide, so it has by nature a very, very high content of carbon. It's 1.4% in 6.14% in theory, but during sintering we get different stages, different amounts of carbon, and it is quite important to distinguish here between 1.2 and 1.3 and 1.4%. And in order to receive such accurate results, you need very reproducible, very good repeatability in the analyzer. And we are proud that we manage it with a deviation of 0.1% or even less for this sample material. So it's a matter, of course, of the lens management on the power settings, but also of the cooking recipe with the accelerators. Later on, I will present you our application notes where those things are described, but for now, let me please just show you the very repeatable and very reproducible results we get for tungsten carbide. Also for steel and iron, we have such repeatable results. If you go for machining steel, which has typically a medium-high carbon content of 0.6% roughly, we get a very good deviation here, and also the high sulfur content of 0.2% can be is found very reproducible with a deviation of 35 ppm or 30 ppm only. It's different for case hardening steel. There we have less carbon and less sulfur content, but still we get it in a extremely good deviation of less than 1% with 0.5 and 0.9%. It is important to make measurements and to get reliable results which are only driven by the content you have in your sample and not by the general deviation of the instrument. Thus, a good method, a good instrument, a good detector is very helpful. And with the Ultra CSI, our customers have the right tool at hand to receive such repeatabilities. Also for highly alloyed steel, which is more resistant, of course, where you need more power, and also you need a little bit more repeatabilities to measure it here in a good way. And even although we have quite small amounts of roughly 500 ppm carbon and 160 ppm sulfur only, we receive results of much better than 1% for carbon and roughly 1%, about 2 ppm for sulfur. With such results, it is possible to produce good steel, to use it in typically highly alloyed steels are used there as well in additive manufacturing, and to gain the quality your customers ask you for. It's not only the final product which needs to be tested, it's not only about the result itself, but also the way how you receive the result is important for many customers, because all of you operators usually comply to one of these international standards. It might be ISO, it might be ASTM, it might be DIN in ISO norms, which are used for many metals, like for steel, steel iron, ores, soil, or refractory metals. So for each type of metal, there is a certain norm available, and it's recommended that the producers and the users in their analysis laboratory follow those recommendations in order to be compliant, in order to meet international quality standards. Since Ultra actually complies to all relevant norms in the field, I'm not mentioning all of them, but I pick one of the most important or the mostly used, most typical norm out. It's the E1019 ASTM norm, called Standard Test Method for Determination of Carbon and Sulfur in Steel, Iron, Nickel, and Cobalt alloys. So this is a very typical one, and the next slide shows you first on the left side how ASTM requires the setup of an analyzer used for that machine, with carrier gas cleaning, with the furnace, with the detector. And on the right side, you can see a scheme how our analyzer CSI is working. Actually, I will not go too much into details, but it's important, but it's enough to show you that we don't only comply to it, but obviously during planning, during constructing our analyzers, we did it with the idea to be compliant to international norms. So by selecting our analyzer, you can be quite sure that you meet those standards. And if you should not find the norm you're looking for in one of our brochures or advertisements, don't hesitate to contact us, because we didn't put all of them in the list. Maybe we are not even aware of all of them because we are not in the metal field as detailed as you are, but we have all the norms available and we can inform you if and how we comply to those. So if you don't find us there, don't give up. Just let us know. There is a pretty high probability that we comply to those requested standard as well. Besides those instruments and high quality consumables, we also offer a service in order to help our distributors, our service technicians, but mainly our customers in their daily work. Altra offers brochures and technical info. The brochures are probably interesting to get a general overview, but the technical information are collections of articles about certain fields of analysis. Here, for example, shown the solutions for additive manufacturing and powder injection molding with our analyzers. Not only ours, you will find also articles from our sister companies like Wedge, Microtrack, QATM, and Carbolite Gero. Further, we have technical articles available on specific topics in our advanced web, available for our distributors on request also for you. And of course, we will comply the most important articles in the download list, which we will make available for you at the end of this webinar. And last but not least, we provide application notes. Application notes is something like the recipe of an analyzers. You can use it as a cooking book. Just check the amount of accelerator you need, of sample you need, how to prepare your sample in some cases, and how to arrange the settings. Usually it is done within a minute or two, and you have the right application which should work with your sample as well. And if you have a special sample where we don't have an application note, of course, Altra also offers something for you. It's online demo, online sample testing. So you can contact us directly anytime. You can contact the distributor. You can give us specific sample materials, and online in our laboratory, we will find a solution together with you how to analyze it. You have to register for such an online demo, and we will make a schedule. We will make with you, and then can start it there, and you can just watch it very comfortably from your desk. This was kind of always available from Altra, but of course, with the recent situation with Corona, this tool became quite attractive for many customers, even which are close in Germany, so they don't have to travel, but can see our analyzers and can make sure how to operate this and how to run their samples with our analyzers directly from their desk or from their home offices. Here on the lower side, you will see our product manager, Mike, who is also answering the chat at the moment, doing such an online demo with the CSI. Yeah. Besides CS analyzers, Altra has also different type of analyzers as well, which might be interesting for you, which will surely be topic of one of our upcoming webinars. We have CS and CHS analyzers for organics as well as for inorganic materials like coal or fuel samples. We have ONH analyzers, which are also mainly used in metal industry for metals, ceramics, or glasses, for example, and also for metal powders. ONH analyzers is a very important analyzer, and we offer the thermogravimetric analyzer TGA, which is mainly used for organic materials to determine moisture and volatiles and ash content of organic materials. So it would be great if you would attend one of our upcoming webinars about those groups of analyzers as well in probably near future. Okay, before I come to the very end of this webinar, I just want to give you a brief overview of Ultra structure. Ultra is on the market since 1981 and part of the Breda Scientific Division, which is a group of companies in the research industry. Our main topic is research of solids, and our sister companies there are Carbolite Gero, Reg, Microtech, MRB, and QATM. And if you use one of those companies, if you are interested in materialography, heat treatment, milling, sieving, particle characterization, you can also contact us and we will hand the information forward to our colleagues from those brands. So now it's time to thank you for your attention, to thank our sales director, Andreas Theisen, and to our product manager, Mike Klucker, for organizing this, for participating, answering the chats. And we are now looking forward to answer the questions you sent us online.